Welcome back to the lecture series of network theory, where we have started learning the application of network theorems in DC circuits. We have already learned the concept of Thevenin's theorem, how to apply them to simplify electrical circuits for independent sources and dependent sources. In the last class, we have already learned the application of Norton's theorem for DC circuits and independent sources. In today's class, we will be learning the concept of Norton's theorem for DC circuits having dependent sources along with independent sources. So let's get started. Now, Norton's theorem in case of DC circuit where we have dependent sources also, it says that any two-terminal active linear bilateral DC network consisting of independent sources along with dependent energy sources can be replaced by an equivalent circuit consisting of a current source which is represented by IN and a resistor. The resistance value of that resistor is Rn. They are connected in parallel, where Rn is the equivalent or internal resistance of the network when we look from the concerned or output terminals with all the energy sources deactivated and replaced by their internal resistances. Now, if the voltage source is an ideal voltage source, then we simply short that path, and if the current source is an ideal current source, then we open those two terminals between which the current source is connected. And IN is the short circuited current through that concerned or output terminals. Now here in this circuit, in this DC circuit, as we can see that we have multiple resistors and we have one independent voltage source, and here we have a dependent source. Now this dependent source can be one of the four types that I have already discussed in that concerned lecture. Now this dependent source can be a voltage source or can be a current source. What we do is finally we represent this circuit by a current source having value IN. Here IN stands for Norton's equivalent current, by a resistor Rn, Norton's equivalent resistor, and they are connected in parallel. Now with that simplified circuit, if we reconnect the load resistor or concerned resistor that we removed in the first step, then the circuit will be a complete circuit. And now if we want to find out the current value, suppose that flows through this load resistor, then current value I will be or can be calculated like this. Here the IN will be divided into two parts at this point. So when we will find out the current value which flows through this RL load resistor, then we will apply the current division rule. So here it will be simply the opposite resistance Rn divided by summation of both the resistances Rn plus RL into the main current or the current of this current source, which is IN. Now next I will discuss about how to Nortonize an electrical network, or how to find out the equivalent Norton circuit of the given DC network. So here as we can see that we have a resistive network where we have an independent voltage source and where we have also a dependent source. Now this is our concerned terminals across which this load resistor RL is connected. So in the first step, what we will do is we will remove this concerned resistor through which suppose we want to find out the current value. Then after removing this load resistor between these concerned terminals, we will short that path, and after shorting that path we will find out the short circuited current that flows between these two terminals AB, and that short circuit current will be called as Norton's equivalent current of the whole circuit, and that is the current that we represent in the final or modified circuit. Next we will open those two terminals and then we will find out the open circuit voltage between those two open terminals A and B. Now after obtaining the short circuit current ISC in the second step and open circuit voltage VOC in the third step, we will simply take the ratio of VOC and ISC. So this voltage, the ratio of voltage and current will give us a value of resistance, and that resistance is our Norton's equivalent resistance that we connect in our final circuit in parallel with that current source that has value IN. Now in the next step, we will connect that IN, the current source, and RN, that resistor, in parallel. And after connecting these two components, we will reconnect the load resistor RL that we removed in the first step. And after connecting these three components, next we will find out the current value through this load resistor or concerned resistor by this formula. So here I will be the opposite resistance Rn divided by the summation of both the resistances multiplied by the main current. Here we are applying the concept of current division rule. Next, we will simplify two electrical networks by applying the concept of Norton's theorem. In this DC circuit, we can see here that we have an independent voltage source having value 10 volt, and along with that we have also a dependent voltage source having value 2I. Now I is the current which flows through this 2 ohm resistor, and from the polarity we can easily say that this is a voltage source. Now we have to find out the current value which flows through this 4 ohm resistor. So this is our concerned resistor or load resistor. Let's mark this as A, this terminal, and this as B. So between these two terminals the load resistor is connected, and we have to find out the current value. Now in the next step, what we will do is we will remove this load resistor having value 4 ohm, and then we will simply short those two terminals AB. Initially, when we had 4 ohm resistor in that circuit, the current which was flowing through this 2 ohm resistor has value I, and based on that the dependent voltage source has value 2I. Now since we have removed this load resistor and we have shorted that path, that means the current which will flow through this 2 ohm resistor will not be same as before. So let's take this as I1, and accordingly the value of this dependent voltage source will change to 2I1. Now next our task is to find out the value of this ISC. Now here from this part of the circuit we can see that the voltage value of this voltage source which is connected between these two terminals is 2I1, and voltage value across this resistor will be simply 2 the resistance value multiplied by the current value ISC. And since these two components are connected between these two terminals in parallel, that's why the voltage drop across this 2 ohm resistor and the voltage value of this voltage source will be equal. So that's why we can write this way: 2I1 will be equal to 2ISC. And from this equation we can conclude that I1 will be equal to ISC. Now if we look at the left part of this circuit, here we can see that these three components, this independent voltage source, this resistor, and this dependent voltage source, they have formed a loop or complete path. So we can simply apply the concept of KVL in this loop or mesh, and we can find out the value of I1. Now in this loop, if we start traversing from this point, then we are traversing this voltage source from negative terminals to positive terminal, and if that convention is taken as negative, that means the value of this voltage source, if it is taken as negative, then after applying KVL, the equation that we will get from that loop, it will be minus 10. Then the voltage drop across this resistor, which will be 2 multiplied by I1, and since current is flowing in this direction, so current flows from higher potential to lower potential, so with respect to the direction of current, this will be plus and this will be minus. So in the equation it will be taken as plus 2I1 value of this voltage drop across this 2 ohm resistor. Now if we take the voltage value of this voltage source, then we are traversing from positive terminal to negative terminal. So value of this voltage source again will be taken as positive, and the algebraic sum of this all these values will be equal to 0. So from this equation we can say that 4I1 will be equal to 10, or I1 will be equal to 10 by 4, so it will be 2.5 ampere. So if I1 is equal to 2.5 ampere, then we can also say that ISC, short circuited current, or Norton's equivalent current IN will be also equal to 2.5 ampere. Now in the next step, our task is to find out the voltage drop across these two terminals after opening that shorted path or after removing this load resistor. So after finding out the ISC, short circuited current, our next task is to find out the open circuit voltage between those terminals. Now here again, after removing this load resistor and after making these two terminals open, definitely the current that will be flowing through this 2 ohm resistor, this will be again not same as I. So let's assume this variable as something else, and that is I2. Again, that will not be same as I1, because in the previous case this was a shorted path and here it is an open circuit. These two terminals are open. So this I2 will not be same as, neither same as I nor same as I1. So this is I2, and accordingly the value of this voltage source will be 2I2. Now since these two terminals are open, that means no current will be flowing through this 2 ohm resistor. So we want to find out the voltage drop across these two terminals. So since no current is flowing through this resistor, so no voltage will be dropped across this resistor. So voltage drop across these two terminals will be same as the voltage value of this voltage source. Now here the voltage value is 2I2 and still the I2 is unknown. So next task will be to find out I2, and based on that we will be finding out the value of VOC. Now again we can see here that this independent voltage source, this resistor, and this dependent source has formed a complete loop or mesh. So again we can apply KVL in this loop, and after applying KVL, the equation that we'll be getting here, again if we start traversing from this point, then minus to plus, it will be taken as minus like before, and then voltage drop across this resistor will be 2I2, and voltage value of this voltage source will be simply 2I2 or plus 2I2, and that will be equal to 0. So here again 4I2 will be 10, or we can say I2 will be equal to 10 divided by 4, that means 2.5 ampere. So if I2 is 2.5 ampere, then the value of this voltage source, since it is 2I2, so it will be 2 in multiplied by 2.5, so it will be 5 volt. And since this 2I2 is 5 volts, so we can also say that VOC, this is also 5 volt. And we know that the RN, Norton's equivalent resistance, is found out from this formula VOC by ISC. So the value that we will obtain as Rn, that will be simply 5 divided by 2.5, so it will be 2 ohm. Now in the final circuit we will have a current source IN, then we will have a resistor in parallel with that current source, and if we reconnect the load resistor RL, then this will be the modified or the equivalent Norton's circuit, where the value of this current source is 2.5 ampere, the value of this Rn is 2 ohm, and the value of this load resistor is 4 ohm, and our objective was to find out the current value through this load resistor, which we took as I. So this I will be the opposite resistance 2 divided by this two summation of these two values 2 plus 4 multiplied by the IN, which is 2.5. So it will be 1/3 of this 2.5 ampere, and that will be 0.833 ampere. So this is the current that flows through the load resistor or concerned resistor 4 ohm. Now in the next example, again we can see here that we have a DC network having 3 resistors. We have an independent current source having value 8 ampere, and here we have a dependent current source. From the direction from this arrow we can say that this is a current source, and the value of this dependent current source is 4I, where I is the current which flows through this 3 ohm resistor. And we have to finally find out the power loss across this 8 ohm resistor, and by applying Norton's theorem we have to find out that. So this is our concerned or load resistor which is connected between these two terminals AB. So in the next step we will find out ISC, and then in the next step we will find out VOC. Then by the help of those two values we will find out RN, and then in the final circuit we will reconnect IN or ISC and RN in parallel, and with that connection we will reconnect the load resistor. So we will now solve this, simplify this circuit in step-by-step manner. So in the next step we have opened we have removed this load or concerned resistor 8 ohm, and we have made these two terminals open, and we will now find out the open circuit voltage between these two terminals. Between VOC and ISC, anything we can find out first. Now after opening these two terminals, the current which will be flowing through this 3 ohm resistor, definitely it will not be same as before. So the current now has been assumed as I1, and accordingly the current value of this dependent current source has been changed to 4I1. Now VOC, this open circuit voltage, as we can see here, that through this 1 ohm resistor no current is flowing since this path is open. That means the voltage which will be dropped between these two terminals, or we can say the voltage which will be dropped across this resistor, will be the measurement of this VOC. Now to find out the voltage drop across this resistor, we have to first obtain the value of this I1, then we can multiply this 3 ohm resistor with that I1, and we can find out the voltage drop between these two terminals. So here as we can see, when this path is open and no current is flowing, still we have these 3 branches which are connected in parallel. So here we can easily apply the concept of KCL, and we can find out the voltage drop. Let's assume the potential of this principal node is V1, and potential of this principal node which has been assumed as reference node is 0 or 0 volt. Now at this principal node, if we apply KCL, let's say this node is C. So if we apply KCL at node C, then as per KCL, the summation of all the incoming currents will be equal to summation of all the outgoing currents. Now here, as per the directions given in the main circuit, we can say here we have only one incoming current with respect to this node, and all other currents are outgoing currents. So simply the equation will be 8 will be equal to then the current value through this resistor, and that will be the voltage drop between these 2 points, which is V1 minus 0 divided by the resistance value, which is 3, plus the current value which is flowing through this dependent current source, and that is 4I1. So 4 multiplied by I1, where I1 itself is V1 divided by 3. So it will be V1 by 3. So if we simplify further this equation, then we will be getting V1 plus 4V1 divided by 3. So it will be 5V1 will be equal to 24, or V1 we can say it will be 24 by 5 volt. Now since V1 is 24 by 5 volt, and that so the voltage difference or potential difference across this 3 ohm resistor will be V1 minus 0, that means V1 itself. So the VOC, measurement of VOC or value of VOC, will be simply same as the voltage drop across this 3 ohm resistor. So it will be 24 divided by 5 volt. Now our next task is to find out the short circuit current after sorting these two terminals. So this is the circuit, how it will look like after sorting these two terminals. Now since we have sorted, now this time this is a complete path. So current will flow through this 1 ohm resistor, and the current value through this 3 ohm resistor will change. It will be neither same as I nor same as I1. So it has been assumed as I2, and accordingly the current value of this dependent current source is 4I2. Now again this component is in parallel with this. That means in this circuit we can say that all these four branches are connected in parallel. So here again we can easily apply the concept of KCL and we can find out the desired value. Now here this principal node, again if we assume that the voltage or potential value of this principal node is V2 and potential value of this principal node is 0 volt, that means reference node it is, then if we apply KCL again at that node C, then it will be again summation of all the incoming currents. Here this is only the incoming current and all other currents are outgoing current with respect to this node C. So it will be simply 8 will be equal to, here the current value will be again V2 minus 0 divided by 3. Here the current value will be 4I2, so it will be 4I2 itself is V2 divided by 3, and here it will be ISC. And other way we can say that it will, the current value through this 1 ohm resistor, that means ISC will be equal to the potential difference, that means V2 minus 0, so V2 and then divided by the resistance value, so it will be simply V2 divided by 1. Now if we simplify further, then it will be 3, it will be V2 then 4V2 then 3V2. That means we can say that it will be 8V2 that will be equal to 24. So we can say that V2 will be 3 volt, and we wanted to find out the short circuited current through this path between AB. So since V2 is 3 volts, so we can say that the voltage drop across this 1 ohm resistor will be also 3 volt. And if we write that the voltage drop across this 1 ohm resistor is 3 volt, then it will be equal to the current which is flowing through that 1 ohm resistor, which is ISC, and then the resistance value. So it is 1. So we can say that ISC will be simply again 3 by 1, that means 3 ampere. So far we have obtained the value of VOC, which is 24 by 5, and the value of ISC, which is 3. So easily we can find out the Norton's equivalent resistance, which will be equal to VOC divided by ISC, and that will be 24 by 5, and here the value of ISC is 3, so 24 by 15, so it will be 8 by 5 ohm. So this is our Rn, 8 by 5 ohm, and value of In is 3 ampere. So if we draw the modified circuit or the final Norton's equivalent circuit, then it will be our In, which has the value 3 ampere. Then with that Rn will be connected in parallel, which value we obtained as 8 by 5 ohm, and with that we will reconnect the concerned resistor which has value 8 ohm. Now the requirement was to find out the power loss across this resistor. So first we have to find out the current value through this 8 ohm resistor, and that current value will be 8 by 5, the opposite resistance, divided by the summation of these two values, then multiplied by IN, and which is 3. So if we further simplify, then it will be 8 by 5 and here 5, and then it will be 48 and multiplied by 3. So it will be 6 and finally it will be 0.5 ampere. So this is the current value, and power loss across that resistor will be simply I square R. So it will be 0.5, that means half. So if we take the square value, it will be 1 by 4, and then the resistance value 8, so it will be simply 2 watt. So this is the way how we can simplify a DC network where we have dependent source along with independent sources by applying Norton's theorem. So with this I end today's class. Thank you.